How do you see it? Okay. Anybody else need 7? Chapter 7. Oh, no. Anybody else got it? Yeah, better. There's just so many contracts like that. Yes, sir. Pretty much, yeah. Is it page 15 or slide 15? Slide 15. Example 6.1. Okay. So we actually did this calculation. Yeah, we did. Yep. The battery for like. Okay, so let's pull the batteries out. They need to go in there. Yeah. And then we'll look at the types. Okay. See what size they are. And then I'll they're a couple. Okay. So we've been talking about those electromagnetic waves. So we also know that so we also know that those are going to be the longer wavelengths. So we'll also think about so I know you guys are thinking that first thing that popped in my mind. Oh, right? So AM stands for amplitude modulator. What do you guys think that means? Okay. A little oh, because you guys have the okay. So what do you guys think AM stands for? So scoot scat. Amplitude. Amplitude, yes. So it's amplitude modulating, right? So amplitude modulating basically means the amplitude is modulating. You guys remember what the amplitude is? The what? The first part of the wave. The first, okay, so half of the wave. Take half that wave, how high it goes up, that's the amplitude. So if we take a look, here we have our amplitude modulating, right? So we have it in some cases where we have very high amplitude. In other cases, we have very low amplitude. But we notice that the wavelengths are changing. Right? So you're not so in other words, in that case, higher frequency. Closer together, they get further apart. Closer together, they get further apart. So those are your two examples of your radio waves, right? We're familiar. So when we talk about interference, you guys know what interference is?
That's when like a radio picks up another radio signal or something like that.
Okay. Yes, that would be an example of interference, right? So there are two forms of interference, right? There's what we call constructive interference, and there's destructive interference. Okay, kind of makes sense. One being constructive, one being destructive. So constructive interference basically means that you're adding to, right? So in that case, you have two waves. If you have two waves that are exactly the same, you're just going to increase the amplitude, right? Because they're going to be adding to each other. So you would increase the intensity of light or sound. Thinking about radio waves. Okay. Now, destructive interference means that it's kind of canceling each other out. So it can cancel each other out if they coincide specifically. I'll give you an example. If they coincide exactly, like your top and your bottom are right on top of each other, they're going to cancel each other out. Right? Or they can just partially cancel each other out. And so, in other words, in those areas we're thinking about light, those areas will be dark. Okay, so let me give you an example. Okay, so here. Let's go back. Okay, so here, you guys see the dark spots here? Right. Yeah. So those will be example of destructive. Here, these will be examples of constructive. So your intensity is getting greater in that case. So in other words, those waves are right on top of each other, so you're getting a stronger signal. Okay.
So would it be more clear as well too?
What was that?
Would it be more clear, the signal?
Not necessarily. It typically is just more intense, the intensity. It doesn't necessarily be clear. Now, and when you see the other cases where we have I keep forgetting you guys can't see over there, right?
No.
They just make me want to work all the time. They're like, oh, you're too fat. You need to get some exercise, get the steps in. It's West Hill's fitness program. He's not good. I was very yesterday. Okay, so let's say we're talking about this way, right? So if they have an exact overlap, right? Where one is going up, the other is going down. So if the wave is in the trough, peak, they're going to cancel each other out. Those signals are going to add up to that. So you're going to get black space. This guy is going to be equal to more 10, right? Because Peaks are matching up with peaks, troughs are matching up with troughs. So there's no canceling. It's going to be an additive. And so in the case where we have partial overlap, we're going to get some signal, but it's going to partially cancel each other out. So this here is going to cancel out with each other because this is a peak and that's partially trough. But the areas that we have together, that's going to give us a little more intensity. Right? So that would be the case of that little bit of light in certain places. We get partial canceling. Okay. Questions? Okay. Standing waves. So when we talk about light waves are traveling waves. Why do you think about traveling waves? Travels, right? You know how fast it travels and everything like that. Standing waves are when waves are stationary. So in other words, they're going to be stuck between 2 points. Right? So when we think about electrons being excited and dropping back down, they're going to be stuck between those 2 points. That's an example of He's a bird. Okay. So if you guys think about it, vibrating string. It's like when I'm looking for stuff, I can never find stuff, right? So everything's recorded. Did I do that or did I must be in trouble. They got the comments that I said earlier. So the one or the other. Okay, so if we do this, that's not working. Okay, I'll pull mine. All right. Okay, so we got a little bit of a wave going on, right? Okay, so this is an example of that vibrating string, although it doesn't want to work for us. The string moving up and down between 2 points, right? So that would be an example of a standing wave. Now, this will be an example of a single dimension because it's only going in this direction, right? It's not going this direction, okay?
Does that have to stay between the 2 points as well?
That's right. So here are examples. Those are our 2 points, right? And so we can have that big long wave, right? And then we could have, you know, a full wave, and then we have. So those are going to be where the first one does it have? Second one has 1, and the third one 2. The next one has 4, 3. Right? Or no, not 3. 1, 2, 3. Yeah. Okay. So when we think about the electron jumping, right? That jumping is the nose. It's being stuck within, you know, where the atom, where the nucleus starts, and where technically ground state, and where the farthest part is. Right? It's going to be stuck between. It has to stay between. Okay. And so in that case, you have no. Okay. So on the side, that's called the what? The numbers on the side. 1 to 7. What is it called? Periods, right? So your periods are going to be representing your numbers, right? So Period 1 is going to be your first number. Period 2 is going to be your second number. Period 3 is going to be your third number. Period 4 is going to be your fourth number. So you take your while to find out. All right. You found everything else, right? Five is going to be the fifth number, right? So when those electrons are moving, they're going to be moving up to those periods, right? So this is an example. Those nodes are an example of quantization, right? So they're kind of like steps, you know, where 1 is the first step, second step, third step, fourth step, fifth step. When we think about a line spectrum is an example of that step function, right? Where a continuous spectrum, did I guess, did you guys this classes yet? We love her. I don't know. You managed to bring some incredible stuff. Okay, so now put on the glasses. Everybody have the glasses on?
No.
Your style and profile it, right? And then don't look directly at the light, look next to the light. What do you guys see?
Ooh, like a reflection. Yeah.
So you see rainbows?
Yeah.
Everybody see rainbow, right? Now tell me about that rainbow. Do you see specific lines? Or do you see it flowing into each other?
Flowing into each other, gradient.
Well, there's two different.
They're separate blocks, but they overlap.
Yeah, I see them.
One
where they overlap.
But even the one that fades, you said that they're blocks, right? They're just all kind of flowing to each other.
Yeah.
You don't have one line,
No.
not taking two lines, and not taking three lines, then nothing. Okay, so that's an example of a continuous spectrum. Okay, so you guys are checking out a continuous spectrum. You guys are super cool. You're going to keep them for the lab. You're going to use them. But you can take them off now. So,
what if they magically disappear?
I'm going to magically come after. Does that answer your question? No. Change your address.
I mean, I think it's.
Oh, he's already told you, you know, and Avenel ain't that big. I definitely can find you that.
It's okay.
Take you to his house.
Man, we just been.
He doesn't know exactly where I live.
I know the street.
I know how your looks.
So
Okay.
There's
So if you
multiple
think
cars
about
like
those
that in my
harmonizing waves or harmonic waves, right? It's going to be the same concept. It's going to be between 2 points, right? So have you guys like pitchfork? You need it to tune your. What's that? Yeah. Yeah, there's some tuning words. Get your pick. picture. Or something.
Oh, makes sense.
You know. Okay, I have to find one for you. There used to be one anyway.
I love that. But the things I can see.
So if we think about a dilated surface, that's a two-dimensional, right? So the one-dimensional wave was our discussed. The dilated surface is going to go, and it's going to be two dimensions, right? We're getting going this way, and we're also going to be going this way. Right? So we got the two dimensions covered. So for a one-dimensional wave, the nodes are going to be like points on the line. And then for a two-dimensional wave, the nodes are going to be like lines on a surface. So two-dimensional waves is going to be these lines. So let me give you an example of that. Okay, so here's examples of two-dimensional waves. But shapes and everything like that. Then, and we're also getting radial nodes, right? So this would be an example of that one dimension. This would be an example of one dimension. Okay. So the black body radiation and it's called TASR. Okay. So black body is basically trying to think of the best way to explain this. Okay. Or an oven that has that electric cord. What happens to that, right? It heats up. And what else happens?
I guess it turns red.
It turns red, right? It turns red or orange or something like that, right? That coils over red. So basically, when things heat up, guess what they're doing? At the same time, they're producing light, right? Because you're getting that orange light. Doesn't it kind of glow orange, right? Yeah. It's a light that we see. Okay. So black light is basically taking the fact that these are ideal nodes. They're going to be able to emit that light. Heat a metal up hot enough, it glows. Have you guys ever a piece of iron? You know, a piece of iron, it's so hot, it'll actually glow blue, right? And so, and you guys, I think I've not seen, I see cars heat up pretty bad where they get that glow to them here on the flag. So something's going to happen, right? Yes. Your car, that's probably what happened to your car that day, right? Okay. So you won't sit there and notice it, okay? Now, the thing is that this will happen. That light also means they kind of go together. And so this here just basically shows us top line represents sunlight. This here basically represents a black body spectrum, kind of like a coil. Those black coils that you have in the oven, as you heat it up, it's called black body. So it kind of matches, but you have some deviations. You have deviations, particularly at that lower end. But other parts of it matches perfectly. Okay, so those upper wavelengths are on top of it, where those lower wavelengths aren't. Notice where the deviations are skewed, the wavelengths, right? Here and at 200 up to, it's about, I guesstimate there 450, right? If you guys look in terms of your spectrum, what is in that area? Let's go back to our other slide. So, so it's that UV range, right? So that UV range doesn't behave the way it's supposed to, right? Where the other ranges kind of fits perfect. And so that's why they say unique catastrophe. You no longer get that matching. So there's something weird that goes. Get batteries to work. Okay, so here's another image. So visible light, oh my gosh, it's almost perfect, right? Looks pretty good. Look at our temperatures. Oh, it's really high and everything like that. We get that blue color. Right? The green. That represents our colors.
Are those thousands or hundreds?
I'm sorry, thousands. Thousands. Okay. Now, the thing is that that's going to hold true for parts of our visible light, right? And as our temperature changes, we're going to get skewing. And we get wave skewing. We don't get anything happening here in that UV range. And that's the part. That's why it's called the unique catastrophe. Now, Planck, physicist, he was like, hey, right? All these experiments and everything like that. We figured out, so we want to figure out that was our energy temperature as a result of energy, right? As we talked about thermal chem already, right? Everybody remember thermal chem, right? That basically is energy, right? So we know that that's energy. So he was doing the science and the calculus behind it. So much energy in, getting all that, right? Why working out? Why wasn't it working out? So in terms of the calculations, and as you guys can also see from my graph, N represents the energy. Okay. H represents Planck's constant. So Planck basically introduced this constant to sit there and try to calculate that energy that we're kind of splitting up. And it kind of compensates for it. It makes that curve look so much better. So then we can sit there and say that energy is going to be equal to NH nu. This represents the frequency, not velocity. So this is Planck's constant. So we know that we can equate frequency with energy. Now, if we look at this equation, if my frequency goes up, what is happening to the energy? It's going to go up because we know that Planck's constant is just a constant. So we know that it's going to go up. As my energy goes down, what's going to happen to the frequency? It's going to go down. So they're directly proportional. Oh my gosh, it worked. It is. Is the photoelectric effect. Now, the problem is that at this point, what we've been using is classic physics, right? So they hadn't really thought about modern physics or modernizing physics. The old way is the best way. That's the only way. That's the way that we've always done it. It's the way we'll always do it, right? That's the mentality that was going on in this time. And they didn't want to look at it any different. They would do experiments, and they would just say, well, they experimented, right? So they do an experiment again. No, that person is an idiot. We got to do it again, right? And so and then they start thinking, well, we need to start thinking about something else. Now, break it down to what it is. It's basically observed when those electrons were being excited. Okay. Now, if I excite an electron, if I put in energy in, depending on the frequency, or depending on the wavelength of the light that we're using, or the energy that we're using, excited, it would eject an electron. If I didn't hit that threshold, it would eject. Now, so this is the photoelectric. The fact that so you got to get over that hump to sit there and make it. Okay. Now, after you get over that hump, then your kinetic energy is going to be dependent on the frequency that's being introduced. And that kind of makes sense, right? Because we said energy goes up when what happens?
Frequency goes up.
When frequency goes up, right? So energy goes up when frequency goes up, okay? So we would assume if energy is going up, we're talking about that kinetic energy. So Einstein basically said that these photons that are being particles that are being released, right? They're being released because we have to put it in the matter. And so he was the one that was the first one to realize it. But what Einstein did, he basically stole Planck's information. He said, know anything, right? So he said he basically used Planck's constant and all the work that Planck did to get to that next step. Einstein got the Nobel Prize.
No longer in that song? Planck?
Actually, I'm sure he made a scuffle, and they're like, no, it was Einstein. But later on, they recognize, they start looking at the data and everything like that. And when they start writing books, they start realizing, and that still happens today. We will learn, like, for instance, the people who discovered DNA, right? Watson Crick and who? Francis Crick and something. Watson. Crick and Watson. So they were credited for discovering DNA. It was actually Franklin. It'll come later. So later on, she gets credit for it after she well passed on. She was the one that basically imaged DNA. She actually took it to them to say, hey, I think I've done it, and he took credit.
Rosalind Franklin?
Yeah.
Thank you.
Looked it up as well.
Yeah. So, and this is how science works, right? She's a woman. Women didn't know anything. They didn't even know their place, right? And I'm not saying that's the case. During that time period, that was the case, right? And it wasn't often when we saw men working in science. And if women were working in science, because she was a technician, right? She had done all of the work. She had done all the calculations. She was the one that did the work. The guy who wasn't doing jack was out for somebody else, right? And there's a whole nice trashy novel on it too. So science, it really during that time period, especially science got a little traction. So things that were going on. They had a lot of time on their hands, right? So anyway, Einstein basically kind of put it back. He said, well, we don't need to worry about the level that's right. Just we're talking about a single photon. Photon itself, in that case, if we're talking about multiple photons, then we need to start thinking about the number that we have. So that energy level, you don't really have to pay attention to, but you have to pay attention to is a single photon, because that's what's going to be emitted from that electron. Okay? And so he said basically E equals HV. And so he basically kind of swooped in and took the guy's credit. If we make some modifications to the equation, we can actually see that here, wavelength, that's right. And we know that that's nu, right? So if we substitute speed of light divided by wavelength into the equation for nu, then we get this equation. So in this case, you think about this. As energy goes up, what happens to wavelength? It decreases. That's right. It's opposite, right? Okay. So we know that it's inversely proportional. Energy is inversely proportional to the wavelength. Actually, go back. Almost there. No, you don't. It's battery effect. Really not. As energy increases, energy is going to increase as more frequency, right? More frequency is going to be happening at the gamma level. And this kind of makes sense. Because we know about gamma radiation, right? It's very high energy radiation. Right? So we know that that must have a very high frequency. That's right. And it must have a very low wave. And so we know that those wavelengths are very low. We've already talked about how much damage they do to cells, and the reason that they're able to do that damage is because they're able to evade the cells. They're able to work I just need to take that slide and put it here, right? Yes. Next is nice. This slide deck is. So, photo effect. This is a result of that. Okay, so this also deals with the fact that we have a wave particle duality. Right? So light travels both in the wave fashion and as a particle. So it's moving, right? So our wave. So here we have a wavelength of 700 nanometers. That's red light. Red light isn't going to be enough to eject an electron. Doesn't give us enough energy, right? We need to get over that threshold. But if we have green light, 550 nanometers, right? Smaller wavelength, it's able to give us a high enough frequency to give us enough energy to eject that electron. But the speed is better than the speed. That's the maximum speed that you get from taking out that electron. And then, if we go down to 400 nanometers, that purplish blue light, right? Then we're going to get an even faster speed. Does that make sense? Energy, right?
Oh.
So it's not necessarily ejected from the wave, it's ejected from the surface. This is a piece of metal.
Oh.
So they did this with metal.
So does it mean that it reflects light? If it ejects it
Doesn't necessarily mean that. So what happens is that if the wavelength is too wide, if it's too big, it's not able to get into the metal enough to actually cause that atom itself to kick out a signal. Okay. If the wavelength gets smaller, it's able to get into that groove to kick out that electron. But depending on how small it gets, it may not have enough room to get it. Smaller, it has enough room to get in there and get that foot. Does that make sense?
Yeah.
So it's kind of like, I think it's a good analogy.
For it to like sneak into the structure almost, it has to be small enough.
It has to be small enough to get in. Have you guys seen Twizzlers, not the Twizzlers, red vines?
Yeah.
Jar of red vines. If your hands are too fat, you can't get your hands in there. Right? You have to get somebody who has small enough hands to sit there and get in.
Yeah.
Right. So that's kind of what we're doing in this system. Different. Because they're really packed in. Okay. So that's exactly what's happening in the case in terms of that metal sheet. You have the atoms, they have to be able to get in the atom to be able to kick out the electron. We know that at this center, the electron is going to be the one that leaves. And so that also means that we're able to go once we kick it out, if it comes back down, right? Which it does, the exciting well, that metal needs to come back to try to be stable, so it's going to come back here. Pull on it. As it gets pulled back down to ground state, then it's going to emit. So we're putting energy in, and we're getting it. But we have to put enough energy in to allow it.
Is it also different depending on which metal you're working with? Yes,
because not all metals are created equally, and their energy levels can be different because how big, in terms of, let's say, for instance, transit is going to be a big we have shells. Right? So it's shells, shells, it's going to be big bottom transit. Where we take something like helium is going to be really small. And we will talk about that. Okay, so we think about so when we see like neon signs, so we're basically observing radiation from the neon signs, and if the radiation that we are observing has a wavelength of 640 nanometers, what is the energy? So in this case, we know that we're going to have to use wavelength because it's given to us. That's true. So, mind if everybody have the question in mind? Yes. That's if the camera decides to work. And it's nanometers. Okay. So, how about I calculate energy? What equation do you guys think I'm going to use?
The photoelectric effect.
Okay, so that is E equals what?
C over wavelength.
Over lambda?
Yeah.
Okay, so
Oh, we can write either way.
So in this case, what is H? What does H stand for? Okay, if I remember correctly, 6.2, no, 6.626 times 10 is 54. Okay, so this is a meter, so that's an nanometer. First thing I want to just do what? Convert. Okay, so how do I convert this to nanometers? I mean, how do I convert nanometers to meters?
Times 1,000, right?
And what?
Is it times 1,000? No.
So, what? 10 to the minus 9. Okay, that's how I remember 9 and both start with N. Okay, so then that means that we have 6.40 times 10 to the minus 7. Yeah, our H, which is 6.6 minus 4 joules per second. And I talked a lot of that you guys can hear later. And we're multiplying it by 3.00 times 10 to the 8 meters per second. Seconds after that. 6.4 times meters cancel out. So we're left with just joules, which are the units for energy. It's going to be equal to what?
.10 times 10 to the negative 19.
Negative 19. Like that. Good. What did you guys get? Okay, so you want me to give you some hints? Why you may be having trouble? You want to make sure to put this in parentheses. Right here. On the bottom.
Oh, okay.
What's that? Okay. Okay, questions? Pretty simple, not too hard. Don't worry about it, we'll make it hard. The 5 step bump, sorry. You just gotta let me know because I'm like, I will erase everything. Yes.
Oh,
Yes. Meters per second. That's going to be. Although I did, I rewrote it. I need
The frequency.
So the relationship of the electron being ejected. Right? So that's going to be our kinetic energy. Right? So that's actually the question. So the question was, what is the relationship between that electron that's being ejected and that photon that's being emitted? Right? So the thing is that the electron that's being ejected is going to be kinetic energy. So that's going to be velocity. So kT is equal 1/2 mass. So that would be the mass of the electron times velocity squared. Or if you guys remember Einstein's equation,
I think that's
E. Okay, so Einstein actually, when we're looking at an individual electron, that kinetic energy calculated by this. Does that make sense? Okay, so if we think about this logically, if that's giving us our kick of that electron, that's what's going to give us an idea of how much energy when that electron drops back down, that should be coming back, right? Because we're going from total kinetic energy so we're going kinetic energy, potential energy, and that always going to have that up to zero. We're going to have to make it out of zero. Okay. So in this case, our complete kinetic energy, right, when it drops back down, it's going to reach its maximum peak. Comes back down, that's going to be our potential energy. When for our potential energy, we're sort of using this. Of the electron. Right? And then it's exciting to say, oh, I'm free, but it's not enough to actually free it because it still has that pull. So it has to come back down to ground state. Okay, so when it comes back down to ground state, it releases that potential energy or the energy that we calculate for that photon. Okay. And this is the funny, this is what I'm like, think about this. It took a long time to say, I remember that you know what this means? You know what this means? What is this really telling us? So if I can excite the electrons in your body, all of them simultaneously, I can make you float. I can transfer you to a little more, right? Because you're at a certain energy level here. If I shoot you with all your electrons perfectly, everything that's in your body perfectly, I can transfer you to that you want, right? So we should be able to teleport, right? If we're able to get those electrons with enough energy, not so much that it kills them, but it has to be uniform enough so that it keeps them together, so we can get you from here to here. And I'm sitting there because, you know, I used to watch. How many of you guys watch Star Trek? Yeah. Star Trek, right? Because you're sitting there thinking, how the hell did they get down to the surface, right? Right? So what that is they should be, you know, exciting the electrons, all the electrons in their body, simultaneously the same energy level, so that, you know, and then so that you stay the more, you don't just pop back, right? So it sounds great on paper. It works great on paper, but have we been able to break it down, right? Elon Musk, that guy, right? He was trying. Yeah, well, he was trying. I don't think he's trying anymore. I think that's why he bought Twitter, right? He's like, I'm done with science. You know, that's just too much for me, right? So really, it's going to be up to you guys to kind of figure out that next level, right? So I'm expecting to be able to test it. I'm sitting on the board right now. You guys can set that. Just sitting on your board, you guys will make a just sitting on your board, I'm going to make a lot of money. That's my plan. Okay, so you guys got to get this figured out. Okay, so before I die, I want to be rich before I die because of you guys, right? Okay, but it's really cool. Now, this whole area, this is called physical chemistry. There's a whole set of chemistry that's dedicated. It's all of it is pretty much theoretical. There's aspects of it that you can kind of test, and that's the concept of that photon being emitted, but that's the extent that we got. Back in 18 something when Einstein and we're not making the progress that we should be making in chemistry. We've made it in other areas, right? Or physics, you know. We need to start making a little bit more. And I think it's my opinion. I'm probably recorded. You know, the government's gonna come back. My government conspiracy. No, it's no conspiracy. I think what tends to happen is that as scientists, you guys listen to us and say, that's not awesome. that isn't going to be able, you're not going to be able to do that. So you got to look at that. I'm not going to discourage you guys from trying. I want you to try. You know, a couple of buildings, it's okay. It's replaceable, right? Just make sure I'm not in it, you know, that's all I care about, you know. But the thing is that you guys got to think beyond that box sometimes, right? And I think we get caught up in the box, get stuck in the box, because people let us get stuck in the box, and we don't believe that, you know, this guy's a fucking idiot, you know, he doesn't know, right? Because if we sit there, if you think about these guys, if they listen to what people were telling them, that go up at the top of the air, sky, you know. I mean, if we listen to what was being said at that point, we would be nowhere. Right? You know, dying is not because you're affected by a bacteria. You're dying because, you know, the devil got you, you know, and stuff like that. I mean, you just think about all of the crazy things that people used to say. Sometimes people still say today, right? You listen to some of the shit that people say. I've heard some crazy things, and I'm like, you know, when the pandemic hit, that's God fighting us. You know, that's God striking those people down. So it's going after the gays, or it's going after the blacks, or it's going after the Jews. You know, and it's usually a result of some anomaly that happens in some genome that causes this virus to be made, right? And it's an anomaly, right? Rather than looking at it like that, it has to be some type of curse on some type of civilization. Now, the curse part is that we got dumbasses that, you know, I'm not good. I want my freedom, right? Oh, God damn, you got to wear a mask. Get over it. Stop crying. Deal with it, right? So, my platform, yeah. My platform. That's okay. I'm going to fix you sometimes. It's my platform. I'm going to get used to it. Then we can have a long, because you're going to tell me what you think I'm full of shit, right? So the thing is that if we impede science by making those restrictions, right, and we get caught up in religion and politics, those are things that keeps us from moving to that next step, right? And so we've got to have to try to learn how to keep. I mean, politics is able to keep science going by funding, you know. Right? Because otherwise we get those various. Yes, we should. And there are stages that we have done that, and then occasionally, I mean, it's kind of history. Yes, we look at history. Throughout history, this has been one of the ongoing battles. Science and politics, religion, science, right? We have this battle for centuries, right? And to me, I'm like, there really should not be battles. Right? But religion should not dictate how science is done, right? I mean, of course, you need morals and ethics. You shouldn't be go killing babies or anything like that. You know, that's morally wrong, right? There's a concept of morally wrong. We need to take that into consideration. There's ethical things that we need to take into consideration as scientists, right? There was because how many of you guys are watch sports? Okay, football. It doesn't matter. People were taking steroids, right?
Yeah.
Was that fair? No, it wasn't fair because they're supposed to be natural talent, right? And them taking steroids, they're enhancing their bodies and everything like that. Although science helped that, right? Science really helped that shit, right? And people were like, hell yeah, we love science at that point, right? Until they started getting the weak, right? So, because we know that steroids basically keeps other things going effectively or cause other things to happen, such as yeah, exactly. Every sport has basically gone through it. And there were time points where people were like, they were debating with themselves. Ethically, is that correct? Right? Is it right to do that? Well, science allows us to do it. So then it becomes a competition with science. Right? Who has the best fucking science? Right? It's not necessarily the athlete. Hey, the best. It's the science that's the best, right? So then there were debates that on it. Well, can we do that, right? You know, and as scientists, we push the envelope. Shake it up. Get you over that hump, over that hill. It's that challenge that we like in science. Oh, and also the money, right? I'm not gonna lie. Money works really well, right? So the thing is that then we started thinking about that, right? My kids, don't want my kids to sit there doping up, you know? And then later on, I wish I would have took that because people don't work anymore, you know, I can't have kids, I can't, you know, all of the other side effects that are associated with it. I mean, those are, it's true. Those are some of the side effects that happen, right? With science, there's always going to be side effects. Have you guys seen all of it? We have medication. We can fix anything today. Think about it. We can sit there. We can actually. You can also do it slightly by getting the. So you start expression of certain genes, right? At certain points. But the thing is that what happens is that you overextend. And so your cones and rods become more. So you get a different color eyes, but you won't be able to see. Right? But that's okay, right? People are okay with that. I don't mind being able to see, right? I wanted blue eyes, right? I wanted blue eyes. Enough people with blue eyes, right? So they're like, oh, fuck it. I don't need that. I don't need to see. So that would make those options consideration. Yes. That's a hard question. I think that is a hard one, right? I don't think there is a cure yet. I do believe that we've come closer. We're getting closer. That's a good question. That is a good question. Yeah, and no, it is a lot of things. If you think about the HIV epidemic, right? Yeah. HIV epidemic is really the drugs. You know, the concept of they can live forever on a drug, right? And you have them for a lifetime. They're going to need it the rest of their life. So they chose to go after the drug more so than they chose to go after the vaccine for curing consent. And that was the interesting. There have been books written on it. There have been scientists discussed it. And scientists that were living with it, right? That were working with it. Now, it changed history. Those drugs changed history. But you have a population that's blood pressure medication. They can say what they want to say. Blood pressure medications. Pretty much going to be on it for most of your life. Very rare that you get an individual because all of the lifestyle changes. It does take lifestyle changes to make that adjustment, right? And it also takes lifestyle changes, and also environmental changes that are factor, which is so you have populations that are going to be reliant on drugs. Concept of wisdom. It was insane. People needed to live, right? And yet you're going to charge them out of the nose, arm. I mean, they're paying. You know, it's, yeah, or just die, right? Or just die, right?
I've heard it as well, like some people get charged like 300 for one dose.
Yeah. Well, 300 was good. They were up to 1,000 for a dosage and stuff. Yeah. It was insane that they were.
And it's literally like $10 to produce a bottle.
Learning to everything and sneeze on them. So, I mean, so we have examples throughout history where, and it's typically, the funny thing is, it's typically not the scientists, right? It is that businessman, right? It is that businessman, right? Those damn business people over there, Mrs. Shepherd's class, right? Go get her, go. See, this is going to get me in trouble one day, right? But the thing is that the scientists may be active, right? But it's not decision where his product, how his product. And so that's why, right? that's why I like talking to you guys about this. I try to talk to you guys about this. You guys need to think about your business. It's your business, right? You guys are designing it. Don't be doing it for somebody else, right? Don't be doing it for somebody else. West Hills has their name on it. Then they have control over how it's going to be managed. You want to make sure that you make the decision how much it's going to cost. So then you have the right? Because if you let somebody else do it, typically they're going to be unethical. But people or society is going to you. They're going to discover. Yeah, that is a perfect example, right? Who was it? So yeah, when they were there together, they were thinking about for atomic energy. That was the purpose that was initially made. The bomb was made for energy. So they said, yeah, let's get something. Right? Oh, hell yeah, let's get some power. And then what do? We use it. And so those are prime examples, right? And it always comes back to that issue. And I really believe because you can see some of the right? Some of the most unethical, unmoral things that people have done. And they, what's that?
No,
that's right. Or Tuskegee. Right? So, yes, not heard of it. So that was basically when, so they had treatment for syphilis a long time. There were populations that were getting bouts of syphilis. It's very common. Some of those folks, right? So, the population treatment with antibiotics, another populations that were getting fireworks. And it just so happened that those other populations were African American. So it was called Tuskegee because it was happening Tuskegee. Somewhere in the south, right? I think it's Tuskegee out there. Don't quote me. Right? In for African American, where in white communities they were giving the antibiotics. And so they were looking at the comparison, and they were looking at the spread of syphilis in that community. And so these people, and they didn't tell them that, hey, we had a hospital that gave placebo or the antibiotic. No, they didn't say any of that. We're treating, right? And so it actually killed them. Of course, it spread. Government never paid for it or anything. This was funded by the government. It was a government sanctioned experiment that was being done. There were never any consequences for it. And this is the thing that get really pissed off when people start bringing up politics again. One of the concept of reparations. There have been so many shitty things that have been done. War, right? And you don't feel that you owe those populations for the shit that you've done. It's kind of like the concept of slavery, right? You built a nation off the backs of people. You owe their descendants the money that they should have been paid while they were in chains. Strictly my belief, but I will argue with the face time. And the nation. And to me, you need to acknowledge that my money. Thank you. I love giving thanks and praise, but money talks. Money. And anybody who is that takes it personally, you shouldn't take it personally because again, you had no say, you had no decision. But that was a government sanction. The government, this country, was good. So that's why right? Think about that social status, that social, and you know that wealth that's being passed on from generation to generation to generation. We had no wealth, right? So you've got to think about those things when you're making those decisions. So it's not necessarily part of its actions. Okay, so let's so let's go ahead and take a 15-minute break. Get a snack since I got out my social box, and then we will come back and do an experiment. Yeah, you never thought that you would get this in chemistry, right? Chemistry is better. Yeah, my grandparents told me, you know, right? And so you sit there, you're growing up, say, it's word of mouth. But you're not taught those things in school. That's like, we want to think of the government as this all benevolent entity, right? And yeah, over time, there have been people that have made decisions that were horrible. Right? And the problem is that there weren't consequences. That's what it might be better at doing checks. Right? So you guys think about what was happening at the border with, you know, kids being separated. Right? It's not, you can't tell me that's right. And the fact that you're going to let this shit happen, and the fact that we let this happen, that was the thing that made me mad. Because I'm like, this is like, built on our second class citizens. You know, and so there are a lot of things that we need to do. And part of it is to have a tendency.
I wish.
Not wanting to address these issues.
Right now would be a good time for like anything.
It is not. It is not this generation that did it. It is other generations. We need to make sure. Right? And so, you know, they want to say, obviously, CRT, but I thought it really happened, right? Yeah. You get some of the paperwork that are in those files, classified files, and now some of them have been declassified. You start to this. Did we really do this? No, we would never do this. That we didn't know that. This what happened with kids being separated. That happens. Right? It happens. It happens. So this is something that's been repeating itself. Right? And yet we let it happen. Sorry, it's bigger. It's not a subject. Wow. That's right. Our mechanism is so slow, right? Look how long did it take them to start chasing the problem. It was years to fix the problem. That shows you that our judicial system is so slow, right? And it doesn't care unless you get money, because money makes everything happen. Look how fast the president gets up. It's already at the Supreme Court. They've already made a decision about it. Because of And that's. What was that? That is maintenance, yes.